that we need to change the place. So in certification. However, there is a small place outside for those just in case that you don't have it, okay? And there is a list that you should sign outside whether you are going to come or not in order to book the appropriate place, okay? Very good. So let's continue the session. No, it's okay. Still, the second talk by David will be online. So now it's Jacobo Barreiro, and he will talk on testing cosmology with optical and radio surveys. So Jacobo, you can start.
Oh, can you hear me? Yeah. First of all, I want to thank the organizers for inviting me to speak at this meeting, my first this cost action meeting. So I'm going to be talking about a bit different topic, more like regarding the cosmology, but it can be related with all the. Oh, did I pass the thing or? Okay. So just to start, a bit of introduction. So basically, from like the boring standard cosmological model, we have this lambda CDM model. Basically, in the last 100 years, we've been building it from different observations and from general relativity, some assumptions, etc. And basically, from the CMB studies, just the homogeneous CMB, then the anisotropies, we got the basically this model was derived from CMB anisotropies, where basically these parameters assuming general relativity with a cosmological constant is the model ruling the universe at the cosmological scales. Then by using these 6 parameters, we're able to constrain the CMB anisotropies. Then we have the supernovae studies of the expansion, basically the geometry of the universe studies with standard candles or standard rulers or now standard sirens or any standard thing you want. You can trace the geometry of the universe, and we also get some basically constraints on the lambda CDM that also agree. Then we have the clustering analysis. Then on the dark matter side, we have lensing studies, the rotation of the galaxies, etc. So basically, we have this thing set up as a standard, even if we still lack a lot of things. But the question this decade, from cosmological point of view, is basically lambda or not lambda. So we probably will be able, before even going to other type of modeling, to discriminate basically if actually this assumption of putting a cosmological constant in the Einstein equations is the right thing, or basically we need to discard it and not just think why with lambda, but also definitely looking for any other theory for gravity. So this talk is going to be basically based on this observable. This is a bit different from the ones that have been described in the previous talks, which is basically the studied lattice structure of the universe, which is similar to basically what was done with CMB, but at all the different scales of structure and at different epochs of the universe. Basically, we're looking at the, I was describing previously the homogeneous universe, but then obviously we are here. We have islands, we have then the planets, stars, etc. So we have inhomogeneities. These inhomogeneities, a part of obviously local effects, depend on cosmology. And then we can basically, we have a study through photons in lensing or CMB, or we can look at the distribution of these galaxies in three-dimensional space. This spectrum has a set of features. These are the larger scales. So basically, the is describing the structure at the larger scales in the universe. And this measurement is relevant because it's giving us information. Anything on the left or at the larger scales than this turnover is telling us basically what the initial conditions were of this large scale structure. So it's talking us about, in the standard model, we have this inflation model, but any theory about the primordial universe, or what we call the early universe science. And we have only measured this with CMB anisotropies. So then with what we call, usually is called large scale structure, which is mostly looking at the clustering of galaxies, we have been able to look at the smaller scale part of this power spectrum, in which basically the structures with respect to the primordial spectrum have been suppressed because of the interactions of photons with the power matter that is described by the standard model of particles. Basically the photons interacting with what we call baryons. And this suppression can be described like this. And this is the part, we call this a transfer function, which is basically how this suppression goes with respect to the initial seed. And then we have observed this transfer function with large scale structure, but we have not reached this part with large scale structure. And the last part of the main part of my talk will be about this and the prospects about doing this as basically a test of different things in the standard model of cosmology. So regarding lambda CDM, it seems that the most data we observe, at least with optical astronomy, we keep finding is the most consistent model with this usually statistical amount of data. So for example, we have the supernovae. So you can do two different things with supernovae. At the lower redshifts, you can measure the local, I will mention it in the next slides, but you can measure the local expansion rate of the universe, which is described by the Hubble constant. But then at larger redshifts, you can see the evolution of the Hubble parameter in what we call the Hubble diagram. And then by doing that, we can estimate the components of the universe, and that's where the dark energy being the most dominating one comes from. And then from the best, so the biggest compilation of supernovae, lambda CDM seems to be the most consistent one with the evolution of the expansion rate in the universe. And then we have here the standard ruler part. So this is basically all the measurements from the current results from spectroscopic surveys, in which we look at the baryonic acoustic oscillations, which is basically in this slide is these wiggles here are reflecting this fluid combined of photons and the baryons that was traveling until recombination, and then it froze on the moment in which photons were freed in recombination, and that scale can be measured at CMB time. But then we can also measure it in the galaxy pattern. You can see as over densities at a given 150 megaparsecs, and we look at that at different redshifts. And by doing that, we can also, I mean, this is the lambda CDM model of the expansion of the universe. And then the low redshift ones agree quite well with the lambda CDM model. And then the high redshift ones that were have been measured using quasar population. In the previous measurements, there was kind of a discrepancy, but in the latest measurement from the EVO survey, they actually went again to kind of agree with lambda CDM. And then now here, this is more related with this conference probably, is test of gravity, direct test of gravity by looking at the growth rate of a structure basically by looking at the distortions in the space of redshift. And then we see also not as well as with the BO measurements, but we see that there is also kind of consistency with lambda CDM. But this leads, for example, the teleparallel gravity that was described yesterday will still be within will be described also by the data. So this is like one of the main tests of gravity regarding the growth of structures. And now we have in the last years we have going farther away from spectroscopic surveys, and we have also photometric surveys that allow us to measure the distribution of dark matter directly by looking at the lensing, the gravitational lensing produced by foreground galaxies. And in this case, in the Dark Energy Survey collaboration, but also with KIT survey, so they kind of give similar results. Also, lambda CDM kind of has been confirmed if you combine with other data, even if you allow the equation of state parameter to vary when doing the fits, it gets close to -1, and all the other things kind of like similar model. I will describe now what happens with the amplitude of the structures, and then also, but not mention it, but yeah, we can put some upper limits on the neutrino masses. But again, lambda CDM keeps surviving new observational techniques. Even if we do parametric, obviously those type of parametric modelings are never perfect with respect to theoretical descriptions, but we can try to do some modified gravity approximations by parametrizing the potential, in this case, the potentials in the perturbation of the Friedmann-Lemaitre-Robertson-Walker metric. Or we can also do, this is actually even simpler, this is just a Taylor expansion, taking the first term and the Taylor expansion of the evolution with redshift of the equation of state parameter of dark energy, which is like, in some models, like quintessential models, will have this kind of shape, but it's just basically parameterization. So currently, the measurements are consistent with lambda CDM again, but as you can see, the error buzzer is still quite big. So there is some opportunities here in the future to try to discriminate. This is part of the main observational prospects for the surveys that are ongoing and in the future in the optical survey. But still, lambda CDM survives. But there is one thing that is basically moving the whole community, which is this the tensions between the data and well, actually the tensions between different data sets. So we measure the H naught doing so the local expansion rate. We can measure it using astrophysics with different techniques. They kind of seem to agree, except with supernovae at low redshift, depending on how you standardize them. But they kind of give a higher H naught. And then when we use the early science, the early universe science, which is mostly CMB or Big Bang nucleosynthesis, we get, and we extrapolate that, this is model dependent kind of, but we extrapolate the early universe to current day, to the late time expansion, we can get a measurement H naught, and there's the discrepancy that is growing and growing, depending on how you combine things. It could be up to 6 sigma, but is usually quoted at 4. And then we have, so this is the amplitude of the perturbations at a given scale. At the time of CMB, this is 10 to the minus 5. This is the famous 10 to the minus 5 anisotropy level. Currently, it's nearby 1. And there is some discrepancy, but actually, with more and more observations in the relation sector, the tension is diminishing. So this tension is not as important as this one. So this can tell us, is this new physics or is this anything given by systematics that we are not understanding? So by now, we haven't, I mean, no, there are several models trying to do this, basically modifying, for example, the dark energy nature by doing some early dark energy models or similar things. And in the systematics field, we still haven't gotten to the point of strain the tension. But also still not from, there is no model that can completely rule out the lambda CDM. And we are still, I mean, there are some non-parametric techniques to rule out lambda CDM and still not rule out by the data, including with this tension. So the title was testing with optical and with radio surveys. Actually, the main point of my talk is going to be the radio surveys. But before that, there is it's not just the future, it's the present. So we are currently taking a spectra with, we started last, actually data started before pandemic, data acquisition, but currently the survey started last March. And basically we will, this will be like the ultimate spectroscopic survey in the optical sector. This prediction on what will be the measurement on the BAO, so the evolution of the expansion of the universe. So it will be the best measurement of BAO. I mean, after that, we will measure BAO again with other types, but this will set up the BAO definite measurement. Then for the growth factor, which is the test of gravity, we'll reach some 1% precision. So we may be able to kind of discriminate much better between models. So this is going to be perfect in this decade, when it's this lambda or not lambda sector.
What do you mean FOR? Which one? Which specific model of FOR?
I mean, I don't know the one that is in this plot, but probably, I mean, you can probably tweak. So I don't think it will discriminate all the models of FOR, but at least you will be able to, yeah. I don't know the one that was using this plot. But yeah, basically so yeah, it will be, so currently it's almost impossible to discriminate the steps of models, but some of them will be, or at least, so the main thing, more than actually getting to this, is if lambda CDM actually is not consistent with whatever we measure, then it will be like rolling out lambda CDM more than actually going.
No, but perhaps there is another model
Yeah.
that is statistically preferable. So you need to use
Yeah.
information criteria. I mean, even if lambda CDM does the job, perhaps there is a model.
Yeah, but you have to fit all the thing. I mean, yeah, it's a combined thing. But yeah, currently lambda CDM is still more. Yeah. Yeah, but if anyway, so what I mean is, with non-parametric techniques, you can like, so it will be super interesting to just know if lambda is not the thing, and if because yeah, you can say it's consistent. But if you rule out, it will be super important. And then we have these two surveys. There is another one, the Nancy Roman telescope, also in the US, that will be a satellite, but yeah, we will have Euclid, which is basically in the infrared. So that means farther away redshifts, and it will be a satellite. It will cover the sample of the sky, and then you have LSST, which is now called the Barreiro Observatory, and this is the survey name. But yeah, basically with those two, we will kind of sample. This will sample basically the southern hemisphere, completely southern hemisphere every 3 nights, because it's going to be looking for transits and all. This is going to be really good also for gravitational wave counterpart in the optical part, because it's going to look at, I mean, the field of view is quite amazing. Yeah, this will close the optical part. So DESI will basically be the best one in terms of at least checking lambda CDM. But then with this one, we will cover the whole optical sky basically. But what happens? This is not the whole thing. So basically, with these opticals, we will be reaching kind of redshift 2. But obviously, the universe has a much larger history. There is this thing that sometimes it's called the redshift desert, which hasn't been explored so much. It has been explored like with individual sources, etc. But sampling the whole time up to the dark ages almost, it will be quite good to basically get the whole picture. And there is this other one thing, which is a part of lambda. There is this piece of the standard model, which is the initial conditions part, that by going to higher redshifts, we will be able to sample these larger modes that I mentioned before that have been only measured with CMB. And we will be able to do a measurement in that same measurement with CMB with the large scale structure using this whole volume, and see if there is some inconsistency, because that's what the H0 tension. Some people think that the H0 tension is because there is some tension between the early universe and the late universe in terms of physics. So we will be able to see if this is true or actually some systematic, because the systematics here are different from CMB. And then obviously there is much more things like trying to measure directly the primordial, the V modes and all that. But yeah, I will focus on this. And then how can we access this redshift desert? This is not multi-messenger, but it's going multi-wavelength, which is going to a larger wavelength mode. So the radio sector, you can access much higher redshifts. So this is kind of a set of future surveys. So for example, this is Euclid that I mentioned. It will reach to something. DESI, also with the quasar population, will reach to something like for these BAO measurements at the higher redshift, and then LSST this. But then with the SK we're starting the 2030s. There are some pathfinders now, but then so in the low frequency mode, we'll be able to reach up to epoch of regionalization redshifts. And then even with other radio surveys in continuum, we'll be able to reach 4 or 5, which may be enough to do the measurement of the power spectrum of the larger modes. So this is kind of the plan for test of the whole model. So the optical part for a quick lambda CDM check, and then this whole one also for a part of the gravity part to check the initial conditions of the universe. And also anything which is relevant for probably all of you, anything affecting the smaller scale part of the spectrum in terms of could be dark matter models or any gravity effect at the smaller scales instead of the larger scales will affect this power spectrum. And the more we sample, we also will get better measurements on the smaller scale part of the power spectrum. And the problem is the modeling, but yeah, that's another thing. But yeah, we will have the data to discriminate between. So, well, this is just one survey I worked on. This is the EMU survey. This is the EMU. So this is basically, so this is escape precursors in what we call the, basically we have the MWA for the low frequency. This is similar to the antenna that was used to measure this edges measurement that in 2018 was done, that they were kind of claiming a detection from the epoch of regionalization, but which currently we think is mostly due to foregrounds. But that basically will tell us about the nature of dark matter. And then we have the ASCAP, which is basically doing what we call continuum survey mode, and then MidCat in South Africa. And then SK will have the observatory here and here too, the low frequency one and the mid frequency one here. For radio, we have so in the same way we have in optical, we have, you can look at the 21 centimeter line of hydrogen and do a spectroscopic survey, but this is a super low redshift when you can discriminate the galaxies. Then you have continuum. Continuum is just observing the whole flux from a radio galaxy, but we have no redshift information. So it's mostly just basically the angular distribution of radio sources. We are working also on trying to get some radial information, and this is the EMU project I will mention now. And then we have the most promising one is this H21 centimeter intensity mapping, which is kind of doing a CMB measurement. So basically an intensity map, but in 3 dimensions. And there is also some pathfinders, and SKA will be also a killer on this. So yeah, regarding the continuum part, we are currently, we're working on this ASCAP EMU. This is going to be the deepest and wider radio continuum survey, probably in the next 30 years, because SK is not going to do a continuum survey, at least not in the first phase. And by doing that, we can do several probes. So we can check, so basically different correlations. We can measure the clustering of these sources. You can see here, so this blue distribution is the dark energy survey distribution of galaxies in redshift. This is what we will get. So you can imagine the volume is going to be much larger with EMU. We are currently covering this part, but we will end. This will be the whole footprint. It's almost three quarters of the whole sky. One thing we're actually measuring with some current quick data we took is the correlation between the photons in the CMB in the larger modes with the galaxy distribution in the integrated search and goal effect. This is a direct measurement of the acceleration of the universe because of the accelerated expansion. When the photons enter the potential and they leave, there is no asymmetry, so you can observe it directly. Then there is the cosmic magnification. This is just looking at the magnification on the flux of background galaxies by the foreground ones. This is also depending on gravity too. And then we can do, this is quite relevant, is the lensing of CMB by this whole kernel. And this is relevant because one of the problem systematics in CMB, also there is a lot of discussion on this, is when you include the lensing of the CMB photons. Depending on how you do that, the constraints from Planck, for example, change quite a lot. And then we have some forecasts for what the sensitivity on the initial conditions. So on inflation, on inflationary theories, for example, constraints. And this is the limit set by Planck. This is what Euclid may do. And this is like the best case we may reach with this EMU thing. So a really sensitive measurement on the initial conditions, and also to compare with CMB again. Okay, well, this is supposed to be gray. But this is the current, so we have currently this data set, which is 300 square degrees. Basically, again, well, this is not a fit. We are doing the fits right now, but basically also the correlation agree kind of with lambda CDM. But yeah, this is quite a small for thing. And also another interesting thing is we have kind of checked, and we have some simulations on radio galaxy distribution, and if we compare with what we observe from here, they actually agree quite well, which is kind of good in terms of the modeling. And yeah, so this is the current distribution, and then EMU will do these 3/4 of the sky. So yeah, we are currently analyzing this. Also, we are doing with a larger quick survey, we are doing this cross correlation with CMB. Hopefully in the next month, we will get these measurements. We already have the measurements, but I mean the actual cosmological results. And yeah, the final part of the talk is I'm going to be talking about the line intensity mapping for tests of cosmology. So basically, this is we have in the 21 transition on neutral hydrogen, and by observing it is not just, I mean, there is several transition lines that you can see in this map. There is also with the carbon oxide and all this, but the most kind of famous one is the 21 centimeter one, at least describing, and we can basically try to well, the main the thing is a part of lying on the radio. Part of the observation is that we can determine the redshift by just observing this line, because we know perfectly the wavelength. But also we can describe the growth, not the growth of structure, but the structure distribution is by tracing the emission from the 21 centimeter line. And at higher redshifts, we cannot resolve individual galaxies, but what we can do is to get a map on the emission from different patches of the sky with the lower angular resolution. We can basically do low resolution maps of the distribution of a structure up to the epoch of reionization. And in the epoch of the reionization, because this is when all these first stars are being formed and all that, this is when dark matter models can be tested quite well, as I will show in the last part. And so this has relevancy for any model of dark matter or any other thing that may affect the clustering at super small scale, affecting directly the structure of hydrogen. So there are currently these different projects. I mean, for its own one, but so basically there is in Canada and China, South Africa, and in some Australian ones too, but not as big. And then in Brazil, there is the Bingo collaboration, and all of them are taking. Well, so there is the Green and Telescope and a bunch of other projects already measured, but these ones are supposed to be surveys, not just taking a small patch of the sky. And then obviously SK and we will do the kind of 3/4 of the sky intensity mapping survey. So we wanted to check how well we can do with some of those in terms of, for example, the growth of structures. So we created these simulations called the H1R4. So we took an embodied simulation, lambda CDN1. So if anybody wants to test another model, we will need to change this part here. So you just do a simulation. Thank you. And then the simulation, you get basically the halo catalog. And then with the halo catalogs, what we did was we created we have some observations of hydrogen populous halos. Before anybody asks about the cosmological influence on this. The astrophysical uncertainties are much larger than any cosmological uncertainty on how hydrogen populates the halos. And we created some mock maps on 21 centimeter. And then, if you remember when I show, well, I can show this one here, but DESI kind of is covering parts of the northern sky. So Tianlai is covering also the full northern sky. So we have at least 15 square degrees overlap between DESI and Tianlai, for example, which is this survey here, which is in west of China. And then we can do cross correlations. Why? Because as you will see, there is a problem with 21 centimeter. Is we have what we call the foregrounds, which is emission from, for example, our own galaxy in synchrotron emission. The foregrounds, we consider foregrounds and noise too. And what we did here was a feed basically to this growth rate of a structure. Obviously, the simulations were lambda CDM, so what we recover is lambda CDM. But as you can see, even with foregrounds, then we apply some foreground removal. Foreground removal techniques have an impact on the of the larger scale modes distribution, but so which may affect, because the way this is fitted is the bias is the amplitude. This is basically how hydrogen is clustered with respect to dark matter. But this is an overall amplitude on the power spectrum, and then this is just a shift on the larger scales with respect to the small ones, so they may affect that one. But if we use 40, well, we use enough resolution frequency beams, so it means redshift beams, we cannot recover the same one. And as you can see, the precision is kind of better than 10%. I'm not showing it here, but we also had some BIO predictions, and we will be able to reach 3% prediction. But again, if you remember the DESI slide, that's going to be 0.3%. So even if a larger one, this is not going to be a killing inbound. And the last thing is we can also do, we just submitted this paper recently. We can, in this case, we chose this ultra light action model. So these ultra light actions, basically what they do is, depending on their mass, so the scale at which they suppress the power spectrum, they produce a suppression in the smaller scale part of the spectrum. And this goes, basically the scale goes inverse with the mass of the actions. So the lighter the action, this ultralight action, the bigger the suppression. So what we created was simulations of, in this case, at the redshift from 6 to 14, simulations of 21 centimeter intensity mapping. And what they do, so depending on your ultra action mass, you change basically the amount of hydrogen, neutral hydrogen that is, well, the hydrogen that is reionized. So this is basically a given. This is basically when you have half of your hydrogen is ionized, and it depends on the mass of this ultralight action. So the smaller the mass, the bigger is this. So the more delay the reionization happens. As you can see here, this is for lambda CDM, and here you still have the redshift 7. So this effect, we can try to measure it. And what we did was we generated several simulations like this one, and we basically did a machine learning approach in which we trained the images, and then what we read observable, these maps. Then we use the test maps to get if we can recover the input mass of the maps. And actually we can. There is a fun result, which is because, as you can see here, for the heavier ultralight action, there is not that much difference with lambda CDM. So even when we have lambda CDM, we recover some mass of the action. That's the thing. But what we found is with 21 centimeter for SK noise level, we'll be able to detect this ultralight action mass if it's smaller than 1.86 10 to the minus 20 electron volts. And if we have no systematics at all, it could be even smaller. So our sensitivity will be better. But some things here, instead of ultralight actions, you can introduce any model producing the same thing. There are different other things that actually exist, like neutrino. Neutrino mass will also produce some effect. So on other matter models. But yeah, this thing could be measured with this 21 centimeter at the epoch of reionization. And in this case, we decided to do this machine learning approach to do this. So take a message is this decade, hopefully we will be able to say if it's lambda or not lambda with DESI, for example. But we should go beyond optical to access higher redshifts, especially if we want to look at the initial conditions of the universe. We are currently working on this ASCAP immune survey that in the next months we have the first results. In the next 2 years we will have the full results, which we may be able to kind of throw some light on the Hubble constant problem. And then with line intensity mapping in general, but especially with 21 centimeter line intensity mapping, we can go to higher redshifts. We can try to check this evolution of the growth rate at larger, higher redshifts and check in case some models have the difference of higher redshifts. And then we can also measure in the epoch reionization anything related with dark matter nature, or for example, in this case, we have done that with ultralight actions. But yeah, depending on astrophysical uncertainties, we may be able to place constraints on different levels. So yeah, Evaristo.
Thank you, Jacobo. So are there any comments or questions?
Hi, it's a very nice talk and a very good review in a way. You have mentioned some observations of gravitational lensing effects in different parts of the spectrum, including also the CMB, which is interesting. And I'm wondering whether you are aware if this data or any data that you were talking about were used already to test whether lensing is achromatic as it is supposed to be or not, to look for chromacity.
So there has been some tests on that. In general, infield lensing is the GR1, which will be in this case achromatic. But yeah, in general, so I cannot give a whole. I'm trying to think on paper that explicitly does this, but yeah, in general, so the analysis I show are done assuming the lensing is given by GR. When this, so the. Well, do you remember I showed this slide with the parameterized model? That is just parameter. So this is probably, so I don't know actually if anybody's more expert on FFRs, but if, so this is like an FFR kind of parameterized modeling. So if this, the model that is being kind of assumed has some chromaticity, then it could be checked. But yeah, I don't know if somebody has done that. The one is there is just probably for the, it's just basically, so you have these two potentials in the parameterized metric, and it's basically doing a test of gravity if they are not basically giving one. Oh, sorry, I went. Yeah, here. So this is in, one is the lensing potential, the other is the Newtonian potential, and basically this should be zero in you have normal GR model. If there is some deviations on that, yeah, it can be. So yeah, it can be done, but it needs the formulation. Yeah.
Thank you.
Anything else? Any other comment or question?
Actually, just to comment on this, there is a paper by Ishak on fixing mu to 1, and they have redshift space distortion with Planck data and supernova, and they have a departure or tension with GR. They don't have consistency. If we remove CMB lensing, of course.
Yeah.
And CMB lensing will
move things to.
Yeah. So I wanted to, if you could comment on that.
So I don't know this paper. I may ask you about that. But regarding the CMB lensing, this is why one of the reasons. why I want to do this radio thing is to check how well it is done, because it's also some kind of model dependent. Like, for example, when the CMB lensing is done, the assumption is that the scale structure is quite smooth, but the smaller structure is not taken into account, so that may actually affect that. And if it's actually shifting things, that will be super interesting. But, yeah. So is it Dusham?
Mustafa Ishak.
Oh, yeah, I think it's a recent one, right?
Yes.
Yeah, I think. Yeah, I haven't read that, but yeah. Oh, thanks for that.
Thank you very much.
Is there anything else? Can I ask you a quick question? You know, in many use of these data sets, people are assuming, in order to calibrate their measurements, lambda CDM. So if you have calibrated your data sets using lambda CDM, then if you fit any model, lambda CDM will still win. So on the other hand, the cosmic chronometers are completely model independent. That's why you have these 5 sigma tensions. So I mean, what is your comment on that?
So for this one, at least for the dark energy survey and other ones, in a long time, all the analysis is done blinded. So even so, the data that people is analyzing, you don't even know what. You don't know the cosmology that's been used. Then in DES, we are doing the angular correlations. For angular correlations, you don't need to assume a cosmology, like for example in Sloan or Boss, where you have to go from angular positions on redshift to X, Y, and Z. Here is just array and deck, so it's the angular positions. But then it's done blinded, and actually it's for this reason. So we are trying to get closer to particle physics things. So the plots are shown when people are fitting. We don't even see this. No, so we don't know that. When you do a Monte Carlo fit, actually it's multiplied by some factors. And then we actually unblind one day when we are happy with all the systematic removal and all this, we unblind, and that's what we get. There may be something regarding so I'm not an expert on the chronometers, but so they are cosmological model independent. But I know some people, Armand Schaffelu or some, that they claim there is model dependent, not in terms of like phenomenology, not in terms of cosmology. Yeah. So this kind of thing. But yeah, that's so for this. We are now doing blinded analysis. And for example, for DESI, there's a huge discussion how to blind it. Like if we shift all the data by some unknown thing that nobody knows, so nobody can be like, hey, I don't get the fit I want. Yeah, we're trying to be more particle physicist kind of thing if we can. We still have one universe only.
Thank you. Thank you very much. The next speaker is David Banesty, and he will talk through Zoom. So, hello, David. Good to see you there, and it's a pity that we don't.
Thank you very much. So let me share my screen. Hopefully, it will be fine. 1 second. Okay. So, can you see it? This is fine. Yeah.
Right.
Yes. Okay, so I'm going to start, and hopefully my internet is going to be fine as well. So my purpose, I mean, in this talk is actually to convince you that even, I mean, we discussed earlier like about the H0 tension or some problems in cosmology, but my purpose today is also like to show you that even if we don't have like any observational problem with lambda CDM, still we have an open window to find like new models because we have a lot of fine-tuned problems in cosmology. So as part from this cost quantum gravity phenomenology cost, we actually designed like some model which calls like the Lorentzian quintessential inflation, and that try to unifies the inflation and also the dark energy. I mean, I'll show you, I mean, most of the details, but then you can see that actually there is like an still a gate for new physics or new things beyond lambda CDM model. This is like my purpose here today. So even this is like a simple model, it can be extended or simplified, or the idea itself. So why do we need actually inflation? So I mean, as some people, some researchers already discussed this before. So if we're taking a look on the radiation of the Big Bang, we see this is actually completely uniform. And this is a big problem because, I mean, you need to have some time in order that one side of the sky, like the left-hand side and the right-hand side of the sky, would interact with each other. So the idea of inflation, that before the Big Bang itself, the universe was inflated. So it means like the background itself exponentially grows for a very short period of time, but for 60 folds, as we will discuss. And then, I mean, the two sides of the sky came from the same point, but because of the inflation, they actually pull apart. This was like the original idea. And it was, I mean, designed and extended furthermore after Starobinsky and Alan Guth and others, and Andre and other. So this is, I mean, the idea that before the Big Bang, the universe was inflated for a very short time. So you need like some dark energy behavior before the Big Bang itself, but with a very large energy density. Besides this, we have plenty. I mean, when I'm saying plenty, it's really plenty of new from 1998 signs for that we need to have like a vacuum energy or some lambda, at least lambda, in order to explain the expansion of the universe for the late expansion. So, I mean, so we have like the Pantheon type 1a supernovae. We have the cosmic chronometers that was mentioned, also like the Barreiro acoustic oscillations. And again, all of this is actually completely different data sets. They have different philosophy that related to astronomy as well, or from the ages of the galaxies, or from the changing of the intensity of galaxies. This is like the type 1a supernovae. I mean, you can find what should be the redshift and the intensity, and so on and so on. But still, from all of these kind of data set, you can extract what should be the expansion rate. And the expansion rate is dominated by the dark energy process. Okay, so we have also like before the Big Bang itself, some extension that we need for adding like a vacuum energy, very large one, but also in order to explain what happens in the late universe. When I'm saying late, I mean even like in the CMB, but I mean after the inflationary epoch, we have to add a cosmological constant in order to explain all of the observed universe that so far, that we measure so far. So in order to construct like the models of the inflation, usually we use what's called the inflaton field. So we mean that actually we are using like a regular scalar field. So we have the kinetic term. Excuse me. Okay, so we have like the kinetic term, and we have as well the potential term. Okay, now as we said, we need to mimic like dark energy. So it means that we need like to mimic the potential itself, some dynamical potential that will be dominate for the early universe before the Big Bang itself, in order to have inflation. Okay, that the expansion rate is going to be e to the power of h of t. So if we were right, like the Friedman equations, if we solve like the Einstein equations, and then like assuming Friedman, Lemaitre, Robertson, Walker, that we assume like a uniform space-time, a uniform density space-time. So we get what's called the Friedman equations. So Hubble rate, as you know, this is like the A dot over A. A is the scale parameter. And from the kinetic term, we get like the equation of state of 1 for the kinetic term of the scalar field. And from the potential, we get -1. Now, in order to mimic actually some dark energy behavior, I mean, it could be used also for the inflaton, but also for quintessence, for the late dark energy model. We need that the kinetic term is going to be negligible partially to the potential term. So this is what's called the slow roll approximation. So as you can see, this is like the slow roll approximation. Now, this approximation is not only by the first order. I mean, it's not only by the epsilon, that's the derivative of the potential. By the first derivative is going to be negligible, but also the second and the third and the fourth and so on and so on. So it is natural to define what's called the slow roll parameter, the epsilon and the eta parameters, and there are also like more parameters. You can see like in Planck papers, I mean, all of these kind of definitions. So the condition in order to have inflationary phase, that the epsilon and the eta has to be much, much smaller than 1. And the epsilon has to be also like bigger than 0. So in addition to that, in order to fit what we have from the non-observational knowledge, we need to fit like the initial conditions of the inflationary phase, which like has a temperature, let's say around the Planck temperature, and the temperature of the CMB is going to fit one each other. So this is why after some analysis with the temperature rate, it is possible to show that the number of e-faults, I mean the number of times that the scale parameter is going to be inflated, e to the power of number of times, is going as the following. So as long as we have the potential itself, we can find after this, using this integration, how many times the universe inflated or become bigger, become larger. So the end of inflation is the following. When epsilon, the slow roll parameter, which is related again to the structure of the potential, equals to 1, the number of e-faults is going to be around 60. And the number 60 is related to the temperature rates. Okay, so this is for the homogeneous solution. Beyond this, we can do like the same thing for the perturbations. So we can find, so the idea is the following. Let me tell you about the physics more, like the story more and less about the equations. So the idea is the following, that from the inflationary phase, we had like very small fluctuations. And these fluctuations are actually the building blocks that created the galaxies after. Okay, so the galaxies or the matter that we have in the universe is like the subject that happened after the emergence of these kind of perturbations. So in order to quantify these perturbations, so we have like the scalar perturbation, we have tensor perturbation, and we have like a vector perturbation, and so on and so on. So in order to quantify these perturbations, we defined two parameters. Now, again, there is like some philosophy that related to these parameters, but I want to tell you what is the condition that we want to find with regards to observations. So there is one quantity which calls this the spectral index, NS, and there is another one which is called the scalar to tensor ratio, which is like the ratio in between the amplitude of the scalar of the tensor perturbation over the scalar perturbations. Now, after some mathematics, which is like teached in course of cosmology, it is actually possible to show that NS and R are related to the epsilon and the eta that we found before. Only to remind you, the epsilon and the eta are the slow roll parameters, and that related, to the homogeneous solution. But if you know them, their rate in the beginning of the inflationary phase, you can find the R and the NS. Now, the first one who discussed about inflation is Starobinsky, because he tried actually to modify the quantum fluctuations. So he added like the R squared term. And apparently, if we take like this action and we change it what's called to the Einstein frame, so it means that we can actually transform the metric itself into some scalar field, and the scalar field is going to be like the matter fields that we have on the background. It is possible to show that we have what's called like the whole philosophy that discussed about inflation. We have like on the right-hand side, the slow roll. So you see actually like the slow roll, it means that it's like smooth, but not completely smooth, okay? And so we have like a dark energy domination like in this epoch. And when inflation is actually ends, this is like in this point, and then epsilon equals to 1. And then afterwards, when like the universe is actually oscillating around here, we have like some reheating mechanisms. So we have like a transition in between the vacuum into some order particle creation and so on and so on. So as I told you before, the R and the NS are the important parameters that related to inflation, but there are more, okay? But these are the first ones that usually you calculate. And from the latest measurement from Planck collaboration, we know these bounds on R and NS. So as long as you have the correct model of inflation, as long as you have model inflation and you want to test it, you can test it by using this kind of constraints. So R has to be very, very small. The constraints are 10 to the power of minus 3, even less. And the NS is in around 0.96. So as you can see, this is from Planck collaboration. many other models of inflation are ruled out, but the Starobinsky model of inflation is actually the best one, who sits like on the best. So far is good, but what is the problem that we have about inflation and also like dark energy? As you see, we have a lot of constraints. R has to be very small, NS has the epsilon and the eta has to be very small in the initial condition. Also, like in the late universe, number of was like 60. So we have a lot of fine-tuned problems, and it's like with my supervisor, we try to think how to extend or how to unify the inflationary and the dark energy epochs. Of course, this is not our original idea. I mean, the original idea of quintessential and inflation, how to unify quintessence and inflation. It was by John Peebles and Alexander Vilenkin in this paper. But we actually tried to construct like a model that wouldn't add any additional parameters into the 6 parameters that our universe had. So we can say that this kind of model is like a phenomenological model that does not need like additional parameters. So as I can show you, I mean, this is like one model that my supervisor published, my former supervisor published like a few years ago in 2015. So by using some symmetry breaking or potential, you can see that on the left-hand side, you have like the inflationary phase. And after the inflation ends, you have like the dark energy in the late universe. So this is some like to give you like an idea how this kind of potential are going to look like. And these are the constraints from Planck. So to do like the same thing, here the comment that I want to say that we can construct the models of inflation by using only the homogeneous solution, okay? So we don't have to go like to the perturbations, because as long as you have like an homogeneous solution, you have like the Hubble rate, you can find the corresponding epsilon and epsilon 2, it's like eta and so on, because you assume that they are governed by a scalar. This is like the purpose of this slide. So with Manos, we published some paper some time ago that actually constructs models of inflation by using what's called the scale factor potential. So in this paper, we tried actually to construct what's called the scale factor potential, which means that now we are not focusing on the potential of a scalar field, but on a potential of the scale factor itself. So the energy in this model is 0. And like we are actually approaching from 0 when A is like 0, some finite value, to the right-hand side all the time. Okay, this is not like a V of phi where I can do like some oscillation. No, this is actually some potential that you have to go to the right-hand side. And it is possible to write the Friedman equations in the form of U of A. So only for the dashed line, okay? The Sitter solution, I mean, that you have like a domination of dark energy, this is like an inverse parabola, okay? And even like a matter domination, this is like the blue line, okay? The green line, sorry. And the combination of this lambda CDM, this is like the smooth blue line. So what is the philosophy of this kind of potential? You can find what should be the velocity, the A square, the A dot, as long as you have like some potential. So why this kind of potential is very interesting, and this is what we found, that it does not matter which kind of model of inflation you have. Okay, so here you see like the Starobinsky potential, for instance. Any model of inflation has to have the same initial condition structure, which means like an inverse parabola, okay, because this is like the de Sitter phase. And at the end of inflation, which was like in the slow roll condition, epsilon equals 1, is actually equivalent to the minimal point in the potential. So it means that it does not matter. I mean, you can use like this potential to construct the models that you find. Okay. So as you can see, let me only tell you, I mean, how this kind of form, how this U of A is actually corresponds to this V of phi, the original potential. So here, as long as you have like a very smooth potential, so you have like a de Sitter phase. So this is why you have like an inverse parabola. At the end of inflation, you have a minimal point. And when the universe is actually oscillates, and here that it means that you have like some generation of particle or something like this, particle creation. So in this phase, as you can see, you have like a matter solution. And why do you have actually a matter solution? Because in this phase, when you have like oscillations, so if you do like like an averaging over the oscillations, you can show that the pressure is actually zero, like matter. Okay, so this is like the whole philosophy. Okay, so if you're averaging over the oscillations, you get like a matter solution. That's all. So we try to actually to construct like this one, and this is like a very simple idea that we observed. That if you take a look on the first slow roll parameter, but the first slow roll parameter has a form of a delta function. This is using like the same method that I told you before. If the epsilon parameter has a form of a delta function, so on the left-hand side is going to be very low, that actually is going to be agreed with the conditions that we saw, that we've seen for the initial conditions of inflation, and also at the end of inflation, I mean, like in the dark energy presence, epsilon as well is going to be very, very low. But then you have like some point in the history where actually epsilon is approaching 1. Actually, from this kind of construction, you can find quintessential inflation models. And this was like a very nice idea that you got like in 2020, the Gravity Research Foundation prize. So as you can see, so this is like the construction that we have, like a Lorentzian form. So first of all, this is what we've seen, that if you take like the epsilon and you derive it epsilon 1 and into epsilon 2 and epsilon 3 and so on and so on and so on, still all of these parameters are going to be very small. So it actually means that the initial condition of inflation is actually fulfilled, satisfied. Now, if we have epsilon, we can find what should be the Hubble parameter. Okay, this is only the Hubble parameter for the vacuum. This is without still some particles that you have like, you have to add by some generation or some analysis by itself. So the Hubble is actually get an integration constant, as you see. This is lambda 0. This is actually an integration constant that you get when you integrate over epsilon. So what is the nice idea here, actually? We get what's called the cosmological seesaw mechanism. So seesaw mechanism, as you know, this comes from neutrino physics, that if you have like one particle which is going to be very large, the other particle is going to be can be very light. So in this case, we get that one side of the potential has to be very large and the other side of the potential has to be very low. So because of what? Because of like this exponential with plus sign and minus sign. So the logarithm ratio in between these epochs is about 120 or 130. So now this is actually somehow in the sense of model is answering the question why the inflationary dark energy is very large and the dark energy in the late universe is very low. So I mean, you don't add actually a new parameters, you only rewrite the parameters that you have originally in the form of psi and lambda 0 and gamma. So in that way, you can explain like different parameters in different parameterizations. So why the left-hand side is very large and the other side is very low. So your assumption is actually completely different. So the assumption is like the epsilon. So before we went like to observations, okay, like to test what should be the observation, I wanted also like to test how much this kind of parameterization is really sensitive, okay? So I mean, if I'm given, before I'm going like to observation to do the whole MCNC, here this is only like Monte Carlo without Markov chain, okay? So I wanted like to see that if I have like a uniform prior for a very large values of number of equals, and thank you, okay. And if I have like also a prior of for psi and gamma, so it means that I have a very large possibilities for the initial parameters, and then we can see that the R and the NS, the observables of inflation, are actually sits very nicely on the best values that we see from Planck. So the model is not sensitive too much, even if you take like a very large uniform prior, it does not give you like completely different R and Ns. So it's not too sensitive to the initial conditions that you choose. But again, this is only an idea. Okay, so afterwards we tried like to construct what should be the potential using like some using like the same equations of the scalar field. We got a very yucky potential. Okay, it's not looks very nice. But after some time, I mean, we got in touch with Salu and Decharo that they found with us like better form of potentials. And we also like test this kind of potential. For instance, you can see like this kind of potential that it does not have too many parameters in addition. Okay, it has only lambda and psi, okay, and gamma. So the same number of parameters that we had before. And okay, so in this paper, we also like gave an example for some reheating model. So like in this kind of model, the mass of the radiation, the radiation that comes, the particles that actually decay to radiation goes on the opposite side of the potential. So as long as the potentials become bigger, the field of the potentials become bigger, the mass is going to be lower. And after some time, you have a dependence that the density goes like 1/8⁴, like radiation. So this is what like in this paper. And also like we test these models with, I mean, the last form of potential. We test this like with the latest combination from the CMB and also from the late universe, like BAO and standard candles and cosmic chronometers, and maybe also with Risk prior. And as we can see, I mean, it actually fit very nice to the models. And the difference in between lambda CDM and like this model is not that big. So we can say this is actually like a very nice idea to approach. So, and this is, so let me actually summarize. And this is like the main point that I want to tell you, as long as now we are like in a cost action of quantum gravity. And of course, I mean, inflation is like to assume that you have like the background is classical and you have like some fluctuations, quantum fluctuations on the background. So of course, this is like related to the topic. But what I want to tell you, I mean, also in the sense of cosmology, that even if the standard model of cosmology is like the best model that we have, still there are some open problems in the standard model. For instance, like why the ratio of dark matter and the ratio of dark energy is very similar, or why the inflationary models that has like very small epsilon and eta, and also the inflationary dark energy is very large, and the dark energy in the late universe is very, very small. So I mean, even theoretically, even like we don't have any problem with the observations. The X0 tension is kind of additional effects. Okay, still the standard model of cosmology need to be explained with some further information. So what I wanted like to show here in this very simple model, that you can explain part from it by a very simple idea that the inflation and dark energy are actually unified field, and you have what's called the cosmological seesaw mechanism, and so on and so on. But still, this is like a gate into new theoretical ideas, or more fundamental theories that actually can explain the many assumptions or many fitting that we have like in cosmology. So thank you very much, and I would love to hear your comments or answer.
Thank you, David. Are there any questions or comments? So David, can you tell us what is the minimum value of tensor to scalar ratio that you obtain? So can you go below, say, 0.03 or? Yes, there.
Yes, actually, yes. So I mean, here, this was only like to take, you know, like a very large values. I mean, this is like to test. If I'm taking like a very large values of gamma and psi, you can actually get, I mean, this is like the best pick. But as you can see, I mean, the error bar is also very, is a bit bigger. So I mean that if you go like to the best fit values, okay, I see that I didn't write it down, but I mean, yes, in principle, you can obtain much lower scalar to tensor ratio. Yes. By using this model.
Very good. Okay.
Okay. Thank you.
Anything else? So if not, let's thank the speaker again. Thank you.
Thank you.
Okay, let's proceed with the next speaker, Marco Piva. Okay, very good. So he will talk on inflation, RS normalization, group flow, predictions, cosmology, and quantum gravity.
Okay. Okay. Thank you. Thank you very much. Hi, my name is Marco. I am a postdoc in KBF in Tallinn. My talk would be about how to view inflation as a renormalization group flow, and how to use these techniques, this formalism, to derive some prediction in cosmology in general, and in the case of a specific theory of quantum gravity that we proposed in 2017. So the first part will be about the formalism and stuff. Second part, briefly, about the quantum gravity theory. So I want to start first with a parallelism between quantum field theory and inflation. This anticipates a little bit what I'm gonna say in the next slide, but this is just to have already an idea. So in what is the RG flow in the quantum field theory side will be the slow roll phase in inflation. The coupling constant in quantum field theory will be the slow roll parameters in here, which are, as we also heard in previous talk, small quantities in play here. The beta functions, the analog of the beta function will be derived from the classical equation of motion of the background. The sliding scale mu is substituted with the conformal time, or with this eta, which is rescaled conformal time. The correlation functions in quantum field theory correspond to the power spectrum in the inflation. The analog of Cullen-Zemansic equation will be a specific RG equation which is valid in super horizon limit, and what is the equivalence of RG invariance in quantum field theory in inflation will be conservation of the power spectrum on the super horizon scales. What is asymptotic freedom in quantum field theory? In this case, will correspond to having a spacetime which is asymptotically de Sitter in the infinite past, which is a condition for inflation. And the analog of changing a scheme, a renormalization scheme in quantum field theory, here is the analog. The analog here is changing frame. So let's start with some details about this. First thing I want to say is to define an RG flow, we need mainly three things. A coupling constant that is small in some regime, so we can use perturbative techniques. Then you need a first order differential equation for this coupling in order to define the beta function. And then this is the most important thing, you need a correlation function that satisfies some equation of the Cullen-Zemansic type. So we will see that in inflation we have these three things, and then we see how to use them to derive properties of the spectra. So the small parameter that I will call coupling constant, but this just because it's the analog of the coupling constant, is alpha, and it's defined in this way. So it's proportional to no, it's not. It's related to the slow roll parameter, the square root, proportional to the square root. So this is another quantity that is small during slow roll, and the beta function will be defined as the derivative respect to the logarithm of tau. So this quantity, check. Then, as I said before, from the background equation of motion, you can combine them and rewrite all together to have a first order differential equation in alpha, which is define the beta and gives you the equation to derive the beta. And then you can also define a running coupling constant in the usual way, using exactly the same formula that you use in quantum field theory, and integrating the beta. And then in this paper by Damiano Anselmi was proved that the power spectra satisfies in the super horizon limit this equation, which is formally looks the same as a Kalman-Zemanczyk equation with vanishing anomalous dimension. So we also have this third point, which is the very important one. I also want to mention that this equation can be rewritten in this way, just by seeing the power spectra as a function of alpha k and alpha. And then in the super horizon limit, the dependence on alpha, the running Capri constant, drops. And this translates into this, which just means that the dependence of the power spectrum in the super horizon limit, the dependence on k, is just encoded in alpha. So power spectra depend on k only through alpha k, and alpha k is the running Capri constant evaluated in 1 over k. So let me explain more, give more details about this last third point, meaning the RG invariance of the spectra, and why is this useful. So we can consider in general Mukhanov-Sasaki action for a certain perturbation W. I call it Mukhanov-Sasaki in general. I think Mukhanov-Sasaki did it for only scalar perturbation, but also tensor perturbation has the same an action of the same form. Then you can write it in general like this. So usually you start to do your perturbation, you compute the quadratic Lagrangian, quadratic action for the perturbation in the background, and then you do some change of variables until you reduce everything into this form, where eta is this rescaled conformal time. I place here an h factor, which is a function expanded in alpha. Typically, this h is 1. So to my knowledge, every theory, single field, double field, based on whatever gravitational action gives h equal to 1, except for the theory of quantum gravity that I'm going to talk later. So for now on, h is just 1. And then sigma is another function that is expanded in alpha, and is 0 when alpha is 0. And depends, it is different for tensor perturbation or scalar perturbation, but still appears in this form. So this is the general action. Then usually you have to compute the equation of motion, compute the solution of the equation of motion, and plug them back and find the spectrum. It is important to show, we've shown that the solution of the equation of motion, the Mukhanov-Sasaki equation, can be written, which is this W, can be written in this way, okay, actually eta W, because then later we will see that in the power spectrum always eta W appear, can be written in this way, where there is a function of logarithm of eta plus something else that goes to 0 when eta goes to 0. And eta going to 0 is the super horizon limit. Again, we can rewrite this function as a function of alpha and alpha k. And then from the equation of motion, you would see that this q and this other function satisfy separately two equations. And the solution of the equation for q can be rewritten in this way. So now what we need, this is important because it identifies what is, what are the parts of the solution of the perturbation that actually goes into the power spectrum when you compute it in the super horizon limit, which is the one that is observed. So we have seen that we have this q and this other function j. From the equation of motion, the Mukhanov-Sasaki equation, you can derive q tilde. And from the equation of q, we can derive j. And then, since we know already that the power spectra has to be RG invariant in the sense that I defined before, you already know what is the form given the solution W of the previous equation. What we usually do in standard approaches is that you have this solution, and then to reach that Mukhanov-Sasaki equation, you have to do many transformation of the field and redefinitions, and then you have to do them back to get the right, for example, to get the right scalar perturbation or the curvature perturbation or anything. Here you already know what is the form because it has to be the W, the perturbation, which gives RG invariant power spectra. So this encodes already all the redefinition back that you have to do, but we know now that it has a general form that depends only on J. Well, it has this form. And then if you put it in what you need for your power spectra, you will see that in the super horizon limit, so this is the definition of the power spectra, and this is in the super horizon limit, and it will depend only on Q tilde and J, that, as I said before, you can compute them from the equations. And this is true for every power spectrum. I highlight this with some colors, maybe it's not clear, but this is a general formula, except for these two constant, which depends, and this also, these are the tilts and the running of the tilts and the running of the running and so on. Okay, these are slightly different in the case of tensor perturbation or scalar perturbations. And also this C depends both on if the perturbation is tensorial or scalar, and also on the model, but it's in a very general way. For example, single scalar with Einstein gravity, any potential will give you this C. So it's depending on the model, but in a very general way. Okay, so what is the advantage of treating this, treating inflation with this formalism? We will see now. So the first thing you might think is that, okay, now you introduce this beta as an analog of quantum field theory object, and might be curious to know when you have a potential for your inflation, what is a beta function associated to this potential. And this, you can do it because given the potential, then you can compute all these quantities that I showed before. V was a h a tau minus 2 to the minus 1 power. You can compute all of this as expansion in alpha, or usually they are expansion in alpha or some weird power of alpha times an expansion in alpha. From this quantity, you can derive the beta. This is more, maybe more like curiosity. The more interesting part is if I give a beta, what class of a potential I can associate to a general type of beta. And again, you can compute this quantity and derive the potential. And there is also, I think, an even more interesting part, which is if I give you the action, so I just tell you what is the gravitational action, what is your inflaton, then you can compute not just this 3 quantity, but you can also compute sigma, this quantity that was in the Mukhanov-Sasaki equation, and also the Q and the J. So given the action, you can straightforwardly go to the power spectrum for both. And then from the power spectrum, you can compute the tilts and the running of tilts. You can even something more general. You can even do something more general. So without specifying the action, you just give beta and sigma, which means that you give a beta and you give a Mukhanov-Sasaki action for both scalar and tensor perturbation without specifying from which theory of gravity you derive this. This might be useful for some approaches that are not based on field theories, maybe string theory or maybe loop quantum gravity, I don't know, or maybe just a phenomenological assumption. You need to have a certain Mukhanov-Sasaki equation to satisfy data. So without giving any details about the starting action, you just give beta, sigma, and then again you can derive the spectrum. So we'll see now these possibilities in details. So first, let's start with this, starting from the flow and classifying the potential. So if you, we always assume this beta, at least this beta, means that it starts at least quadratically, and then you classify the potential by setting to 0 this b coefficient. So class 1 is this one. Class 2 is with b0 equal to 0. Class 3 is with b0 and b1 equal to 0, and so on. So you kill all the lower term, and you increase the class of the potential. And so this is the class of the potentials. This is the related beta function, as I just explained. And so in class 1, you obtain V. You always obtain V as an expansion in the field around the value of the field, around the value that the field assumes in the sitter. So here you get constant plus a series in the exponential of the field. Here, class 2, you get some weird power that might be even fractional depending on B1, and then a series in 1 over phi. These two classes has some examples known in the literature. So the Starobinsky model fall in class 1. So many of the known models of single field falls in this class. So Starobinsky, which already belongs to a general class, which is called E model, which is part of the alpha tractor model. They're all described by class 1. The Palatini potential with tangent, hyperbolic tangent square, or to the fourth, I don't remember. It also belongs to another class of alpha tractors, and they're also described by this. Exponential SUSY, mutated inktop, and other that I didn't mention here. In this one, it's a bit more complicated. So it can, in principle, describe very complicated potentials, but you can adjust the coefficient in order to get any polynomials in the field. So these are other class of potential that usually are studied in the literature. So phi to the phi square, phi to the fourth, phi square plus phi to the fourth, and any polynomials you like. And this is also another complicated expansion. We didn't find any potential in the literature that belongs to this class, but we playing with the coefficient, we brought the most general one that I didn't find. I didn't find any paper where they studied this potential. But anyway, this belongs to class 3 as well. Now, in principle, you can continue, but we will see why I stopped to class 3. Then we see this other way of approaching, which is a bit more general. So you start from an action. Now I'm showing you the case of a single field with a general potential. This can be extended to double field, multi-field in principle. So if you start with this very general action, so just Einstein gravity plus a scalar with a potential, then we assume that the beta is of order n, of class n, so we can study altogether all the potentials. And if you do the analysis and work out the spectra and all the measured quantity at the leading order in the coupling constant, then you will see that the tensorial spectral index doesn't depend on the leading order, doesn't depend on any coefficient of the beta, while this one, the scalar one, which is measured, depends on the beta. And you will also find this relation that usually holds for single field inflation to the leading order. If you plug the data, you will see that you will have some bounds for B0 in the class 1, for B1 in class 2, and then so these two numerical bounds, and then any other class is ruled out. So if anyone will come out with any weird potential that belongs to class higher than 2, this is already ruled out, while any potential of class 1 or class 2 has to satisfy this bound, otherwise ruled out again. Then, as I mentioned before, there is even a more general approach that we can have. So without giving any information about the action of the gravitational field and the potential, we just give the Munkaron-Sasaki action for both tensor and scalar perturbation, assuming that these are the only two actual perturbation in the theory, which means that we just give the beta as an expansion, sigma for tensor as an expansion, and sigma for scalar as an expansion. We have this coefficient. I hope you can see the colors. And then if you compute the spectra to the second order, first order, next to leading order, you see that I colored some coefficient to show you where the dependence of this coefficient appear. And some weird things can happen in this case. So you see, this is the scalar power spectrum that you usually have in front of here. So to the leading order, it has a power of -2, alpha to the -2. That's the standard thing you have. And there's no single field theory that produce any other power. While in this case, since we have kept the coefficient of sigmas and the coefficient of beta independent, you will produce some. You can produce this overall factor that has a weird power. Also, in this consistency relation that usually is 0 even at the leading order, now it's not. This is true, of course, if you keep this coefficient unrelated. But typically, now if you want to recover back the results that we already know from single fields inflation, typically the sigma depends on the beta, depends on h, depends on v. So they have a relation. There is a relation between all the coefficients. These two coefficients depending on b and some other numbers. So if you plug them back, you will recover the usual result to the leading order. But this, as I said, might be interesting possibility to already have these results. So we have computed all the power spectra up to next to leading log order. I just showed this order here. So in case there is some phenomenological assumption that tells you need this Mukhanov-Sasaki equation to fit some data, this is how you can compute directly the spectra, knowing this quantity. Now the last part I want to mention, I want to talk about this theory of quantum gravity that we proposed in 2017, was proposed by Damiano Anselmi in this paper using some ideas that we developed earlier in this other paper. This is based on the idea of purely virtual quantum, which are degrees of freedom of a new type that can be introduced in quantum field theory through new quantization prescription. And I will be very short on this because I don't have the time to discuss the details. I just tell you the physics, let's say, on this. The result of this prescription is that you can have a renormalizable and unitary theory of quantum gravity, where you do not propagate any ghost, you just propagate the graviton and a scalar field that you can assume is the inflaton if you want, as in Starobinsky theory. The peculiarity of this fake degrees of freedom of Facon is that they can appear only virtual, as a virtual state. They cannot appear as external state. They are truly not appearing as external state. It doesn't mean that they decay. They cannot, by definition, appear as external state, but still they interact. So they contribute to renormalization. And this is how you can make this theory, which is well known since the 70s, that is renormalizable, also unitary, because usually this term, Weyl square term, will introduce a ghost, which will break unitarity. If you turn this ghost into a Facon with this prescription, and then project into the space where this Facon doesn't propagate, the theory remains unitary, and you don't produce back with loop correction this Facon ghost. This is the reason why this projection is the reason why also in this theory with this prescription, the physical content in cosmology is given just by scalar and tensor perturbation, as in single field inflation. So to summarize, this is what I said. If you have a theory, you want to introduce a Facon, what you have to do is to use the Feynman prescription for any standard degrees of freedom you want to keep as usual. You have to use this new prescription for the degrees of freedom you want to turn into Facon. Then you have to project on the subspace where only the physical ones propagate, and by the construction of all this, it will remain unitary and in the subspace, the theory. And the renormalization properties are untouched. So with this in mind, you can think of extending these models, because the previous model I showed you already contains Starobinsky theory, and then there is this just an additional term. This can be turned into the Einstein frame with into a potential, and then you can think to keep it a general potential and just redo the same analysis. This is straightforwardly applies straightforwardly, and as I said before, it generates this H, which will give some difference in the power spectrum. So you just redo the same as before. You will have some H-dependent terms, so you can discriminate this type of theories from the one which are without the Facon. Of course, the only potential that is compatible with the renormalizability is the Starobinsky one. So if you care about renormalizability, the only theory you can think at the moment is this one, with the Starobinsky potential here. But in general, you can even think about this. And you will have different predictions. In particular, there is a consistency prediction condition on the mass of the Facon. So there is an additional parameter here, and because of the construction for consistency, it has to satisfy this bound. And because of this bound, if you redo the analysis to the leading order, all the throws the potential of class 1 give the same prediction at the leading order. Of course, next to leading order, there will be differences according to the potential, depending on the potential. But they give this prediction for the power spectrum. In particular, if you select the Starobinsky potential, so you have a renormalizable theory and unitary. and you can see that there is this should be blue, but it's not. So the bound is given by this one in that case, and the tensor to scalar ratio has to fall in this region, which is bounded like this. So as you see, it's just slightly less than 1 order of magnitude. This is small for the data now, but it's hopefully can be tested in the next future with Lightbird maybe, or some other experiments that might measure bounds on the tensor to scalar ratio with more accuracy. So with this, I will summarize. With these new techniques, we show that we can see inflation as a normalization group flow. This allows us to use to classify potential and even rule them out. You can use the concept of RG invariance of the spectrum to derive them and derive their properties. And the fact that this is analog with the quantum field theory computations, you can just straightforward using some technique like resumming subleading logs, and with this you can go to very higher, you can go more easily to higher order computation in the parameters, in the expansion parameter. And then with this theory of quantum gravity, you can have a prediction that in principle can be tested in the next future. Something that is left out from this is that not all the potentials known in the literature can be covered by this yet. We don't know, because it might be that they are not suitable for this formalism, and this is where it stops. Or it might be that we need just an upgrade or to do something slightly more sophisticated. Then we can go beyond single field. This was already done in this paper, mixing the Starobinsky potential with the scalar. I think it was pi to the phi square. So it's a mixing of +1 and +2, and we are working on a multi-field where they are all +2 right now. Okay, thank you.
Thank you, Marco. So is there any question or comment? Or from the online participants? Yeah, quick question. I mean, your formalism applies if you are in the so-called Einstein frame that we have gravity plus a scalar field. But in principle, you could also apply it in the Jordan frame, right?
Yes, yes, yes.
I mean, just with
You just have to define slightly different the coupling constant. So this goes to the very beginning. So when you identify these 3 points to define the RG flow, here it depends on which frame you are. But if you want to map this, so for example, you don't have this phi if you are in the Jordan frame. So you have to define this only through the Hubble constant or some function of the background metric. But then the mapping between this coupling constant and the coupling constant that you have to define is just a perturbative redefinition. This is exactly what happens in standard quantum field theory when you use one scheme or another scheme, as I said here. So just this is equivalent of changing the scheme. So you have to define another coupling constant, which is related to the other one in the other frame by a perturbative redefinition. And then once you do this perturbative redefinition, you can just reapply everything.
Very good, thank you.
Okay.
So let's thank Marco again. So the next speaker is Anna Tokareva. She will give the talk online.
Hello, can you hear me?
Hello, Anna. She will talk on 4-dimensional positivity bounds with gravity.
Yes, exactly. Okay, wait a bit. Let me share my presentation. Okay, can you see my presentation? Can you see my presentation? Is it working? I just don't hear.
You can see your presentation.
Do you hear me? Is it okay? Thank you very much for the possibility to give a talk at a conference. I will tell about four-dimensional treatment of positivity bounds with gravity. This is a somewhat more generic topic, which also can be applied to many theories which are called for explaining inflation, gravity, and correspondence between infrared theories and ultraviolet theories. I will be telling about constraints on low energy effective theories, which can be got from assuming that these low energy theories have a good UV completion. The talk is based on my recent work done in collaboration with Mario Herrera Valle, Raquel Santos Garcia. The basic idea behind this work is that if we have infrared theory and ultraviolet theory, normally we know very well what is our infrared theory. We can compute scattering amplitudes. We have Lagrangian for this theory, can find classical solutions, but not all infrared theories can have good UV completion. Normally, we don't know what is the UV theory, and there are just little examples where UV theory can be constructed up to infinite energies. It can be done for normalizable theories, but since we have gravity, then we meet problems with making this theory, which would be UV completion for gravity. What do we? But we can extract a lot of information about infrared theory. We can get a lot of constraints, assuming that UV completion of the theory is good enough. What do we mean by good UV completion? We assume that UV completion should be Lorentz invariant, and for scattering amplitudes, it means that the amplitudes has to be a function of only three variables if we speak about this situation of shell. So it's S, T, and U, and on shell it's only two variables because they are connected. Another assumption for the UV completion is that it should be unitary. So it should be ghost-free theory, which doesn't break unitarity. And this means that imaginary part of the all matrix elements, all scattering amplitudes has to be larger than zero. And this is strict inequality. So besides that, we assume that UV completion satisfies causality, which means that from this condition, it follows that the amplitude has to be an analytic function everywhere except real axis. And on real axis, it might have singularities like poles and branch cuts, which have clear physical meaning, like exchange by massive particles and decays. But except real axis, the amplitude has to be an analytic function, regular analytic function. Then we assume that UV completion is local, has to be local. And from this condition, it follows, it's connected to polynomial boundedness of the amplitudes at large momenta. What we need to build our conclusions is that the amplitude has to grow no faster than s squared at small t. This limit has to be zero. Actually, so-called Froissart-Martin bound, which can be formulated for all massive particles, for all scattering of massive particles, is more strict. It doesn't allow for amplitudes to grow faster than s logarithm of s. This is a weaker requirement, but still it leads to the same conclusions. Interestingly, in weakly coupled string theory, amplitudes have the same properties as they were listed here. It can be taken from explicit expressions of string amplitudes. Due to this fact, this approach can be also treated as kind of swampland constraints, meaning that we are looking for theories which can be UV complete by string theory. But string theory cannot be treated as
Can you come closer to the microphone? But it's not that good.
Okay. Is it better now?
I think yes.
Yeah. Okay. So string theory is not a local theory, but still amplitudes has the same properties. So our results also hold for the case if we assume string theory to be UV completion here. Then why we call it positivity bounds? What is positive? The answer is that the positive thing should be imaginary part of the amplitude. But this is too weak constraint, and we can we can find something more strong, something stronger. Using the analyticity properties of the amplitudes, if we take limit, forward limit t to 0, we can write actually some integral, which looks quite complicated, but it's nothing else but just second derivative at some point, which lies here on the contour. See, here it's a complex plane of S, and we take some point here. Amplitude has two branch cuts as singularities because starting from forum square to infinity and from 0 to minus infinity. And everywhere else, this is regular. This is a regular function. So we can write the second derivative of the amplitude with respect to S as a contour integral of this function. Why we take second derivative? We do this because this kind of integral providing second derivative of the amplitude behaves at large S in such a way that we can neglect large contour. We can rewrite small integral over small contour through integral over large contour plus two branch cuts. And due to the behavior of the bound on the amplitude, that it should grow no faster than S squared, we can neglect large contour. And then the second derivative of the amplitude can be written through integral of imaginary parts of amplitude and the crossed amplitude. The main thing here is that the right-hand side of this equality is positive definite everywhere due to our requirement of unitarity. Even though we don't know what is the theory here at infinity, at infinite energies, we assume that since it's unitary, imaginary part is still positive. And this already allows us to obtain that second derivative of the amplitude is positive. But we can conclude something more, we can make stronger conclusion here because we can even compute part of the right-hand side integral. We can compute its part from forum square to lambda. And write that the second derivative of the amplitude has to be larger than some thing which can be computed in any particular theory, because A of S is something that can be computed until some energy, until which the low energy theory works. Here we don't know what happens, but we know definitely that it's positive. That's why anyway we have here some positive contribution, but we can conclude that anyway, this amplitude would be larger than this integral. And these bounds can be quite powerful. Interestingly, they affect Galilean models, and actually they are relevant for all models which contain higher derivatives. The main contribution of the form S squared to the amplitude, which gives the contribution to a square term and second derivative of the amplitude, comes from d phi to the 4 term. If we don't have this term, then we don't have this contribution to the amplitude. But Galilean symmetry is kept only in the theory without this term and without mass term. And in this theory, the coefficient in front of a square term in the amplitude would be 0, exactly 0. But from these improved positivity bounds, it can be computed that the coefficient in front of d phi to the 4 has to be larger than not even 0, but some computable thing where energy is something close to the cutoff scale. So this is a further a bit smaller than unity. And we have some clear constraint that this term must present in the Lagrangian, but it contradicts to Galilean symmetry, exact Galilean symmetry, which makes it problematic to speak about theories with exact Galilean symmetry, in the sense that they cannot have good UV completion with the properties like with the all listed properties. But still they can be UV completed maybe by some strongly coupled string theory or some non-local theory. The same holds for the same conclusion was obtained for massive gravity. It has low and quite low. It must have quite low cutoff scale, which makes it problematic to see how this can be used for explaining of dark energy. Also, actually, all models with higher derivative terms can get some meaningful constraints from the approach I'm speaking about. In my work, it was done also for model with two scalars, Higgs-dilaton inflation, and in general, all theories with higher derivatives has to be constrained from this point of view. Not all low energy effective theories can be UV completed by something good. But our work extends this approach to the case of massless particles. What I was telling was about massive particles mostly. In the massless case, we have more problems. We have we don't have this picture. We can take the point mu here, but rather instead of that, we have branch cut which goes along real axis. And our approach has to be changed for massless theories, and it can be done if one takes imaginary parameter mu here, and then we can compute the same thing, the similar thing, which also is connected to the second derivative of the amplitude, and again it can be written through some positive integral. Another issue comes if we consider the amplitudes with gravitons. It's even worse than amplitudes for including scattering of scalars and vectors. And this happens because of the fact that the amplitude with gravitons has 1/t pole and the logarithm of t singularity coming from loop scattering through graviton, from graviton loops. It makes it problematic to take forward limit here. And for the second derivative of the amplitude with respect to S, we also cannot take forward limit of the dispersive relation which we used for all these constraints. So let me skip this, not going too much details. For the amplitude containing gravitons, we can also write the same dispersive relation, but it has infrared divergences in the limit of t to 0. And left-hand side has a divergence of the form 1 over t, but the right-hand side is some combination of imaginary part of the amplitude with some positive function. And imaginary part of the amplitude must be a regular function. It cannot contain divergences like 1 over t. And we have a situation that left-hand side of the inequality has 1 over t divergence, and the right-hand side is some integral which doesn't have clearly the part where it can gain 1 over t divergence too. But there is the only source which can produce this divergence. It's an infinite tail of this integral. So we assume that there is an effective field theory, which we know until the scale, which is here assigned as 1 over alpha prime. And after that, we have some tail of the of which for the specific form of the amplitude will lead to the appearance of 1 over t divergence here. And this is the only source from which we can gain 1 over t here. In order to get this, we have to assume that imaginary part has some specific form, which is called Ricci form. And after an explicit computation, one can obtain this 1 over t just coming from integral of this part of the amplitude. In this, and interestingly, this is this choice of the amplitude, which is looks to be ad hoc because we don't know UV theory, but it can be uniquely determined by infrared singularities by means of actually this form appears to be Laplace transform of infrared singularities. And this can be obtained uniquely from the form of infrared divergences of the amplitude. Actually, in order to get this, one has to solve this integral equation, which means that integral of from some scale to infinity from imaginary part has to take the form of a over t, and our task is to find what is imaginary part as a function of z and t here. Under the assumptions we have that imaginary part has to be regular, we can find that the solution looks to be a unique form, at least the asymptotic of the solution and the limit t to 0 and z to infinity can be uniquely determined by the asymptotic of the amplitude at t to 0 limit at small s. So we have, after this complicated mathematics, I can say that just the simple conclusion that we have a surprising connection between the form of infrared amplitude, its divergent part in the forward limit. It's somehow connected with the form of the ultraviolet amplitude, actually determines how UV theory should look like in the case if we want it to be unitary and good in many senses. So from infrared theory, we can deduce what should be the form of the amplitude in the UV limit. Not in all UV limits, because we have two variables, S and T, but in the limit T to 0, S to infinity. So this is infrared form of the amplitude. And from this, we can find that imaginary part of the amplitude in the UV limit, in the limit S to infinity and T to 0, must have this form. If we need to cancel also logarithm term here, we have to assume that there is a logarithm here. It comes just by explicit computation of Laplace transformation. So here, these parameters which enter this form can be also computed from the coefficients of the infrared form of the amplitude. So again, somehow we obtain the deep connection between the forward limit of amplitude in infrared theory with something that we need to have in UV theory. And this form of the amplitude can be also obtained in string theory. It's called Regia form. It appears exactly in string theory, but logarithmic term probably should be obtained when string loops are considered, because in tree-level scattering of strings it cannot be found from explicit form of the amplitude. Then after canceling divergences in the forward limit, we can use the basic technique of obtaining positivity bounds applied to some theories with gravity. Before this work, it was hard to say how to apply all bounds in the case if we add gravity, because there was scattering of gravitons. Which has these terms like S squared over T. Now we know how to cancel these terms, that these poles can be just cancelled with under some assumptions that we have a specific form of the amplitude in the UV, and the rest should get some meaningful constraints. For the very simple theory, the explicit computation for the amplitude is given here. There is its infrared amplitude. Then the second, actually, essentially the second derivative of this amplitude can be also computed, and inequalities gives us the fact that we must have actually, the only constraint which comes in this simple theory is that Planck mass has to be the correct sign. And also we have some connection between parameters standing in UV form of the amplitude with explicitly computable numbers here, like these numbers and these numbers. More interesting constraints can be obtained in the theory, in more complicated theories, and in a recent work by Tolli, De Rama, Alberto, and Jaitley, it was shown that quantum electrodynamics with gravity contains in the scattering amplitude, there is this kind of diagram when fermion loops are considered, and it has negative contribution for a squared term, which actually contradict positivity bounds. The weird thing is that this negative contribution is very large, because there is electron mass in the denominator, and in order to cancel this and keep positivity bounds satisfied, one needs to assume that this Lagrangian should contain this kind of term, and the cutoff scale here, the lambda scale here, should be much smaller than Planck mass. And if m stands for electron mass, it should be 10 to 8 GeV. So it means that in order to make a theory of quantum electrodynamics consistent with which is when it's minimally coupled to gravity, to make it consistent with positivity bounds and with the existence of good UV completion, one has to assume that there should be some new physics at the scale of already 10 to 8 GeV, which is quite surprising. For the pure standard model, the similar considerations were done in the paper by Aoki, Naomi Takuda, Locke, and they obtained that the scale is somewhat higher. The scale where new physics should appear in the standard model, it's 10 to 16 GeV. But this is still a question for discussion, because there is no consensus in the community that these results are correct, and there are no mistakes somewhere on the way. But still, this looks like that the cutoff scale of some renormalizable theory with gravity can be lower than cutoff than Planck mass. So let me come to conclusions. In low energy theories can be constrained from the requirement that they have good UV completion, satisfying Lorentz invariant, unitarity, causality, and locality. In the massless limit, we need some extra assumptions about UV physics to cancel the divergences in the forward limit of amplitudes, especially for gravitons. We have to assume Ricci form of the amplitude to make everything consistent. All this allows to justify the bounds which were obtained without gravity, to say that they also can be satisfied with gravity. And inclusion of graviton scatterings can make the positivity bounds weaker, but due to the terms which are left after cancellations of the 1/T poles. But sometimes there can be, but for some more complicated theories like light by light scattering, some surprising results can be obtained, saying that the renormalizable theory with gravity, minimally coupled to gravity, can have lower cutoff scale than expected intuitively, which would be Planck mass. Thank you for your attention.
Is there any question or comment? So we just said that Galileans are also over, right? Under the requirement of a UV completion. They are almost closed. As your result?
Sorry, could you repeat the question?
Yeah, I mean, so under the requirement of a UV completion, you showed that Galileans are almost closed, right? Is that correct?
Yes, Galileans without gravity are closed from these considerations. Well, closed means that they cannot have good in our sense UV completion. They might have still some UV completion which breaks something. I don't know, maybe Lorentz invariance, maybe locality.
This is not good news. So is there any other comment or question? Okay, if not, we thank you again, Anna, for this nice talk. Thank you.
Okay, thank you for your attention again.
So now we have a lunch break, and remember to sign for a dinner tonight.